right, welcome back everyone. We are going to work on the second part of class, which is going to be taking the next step with our molecular information. So we've done Lewis dot structures, we've done shape. Now, identifying what shape it is from the Lewis dot structure information. And now we're going to move on to the other pieces of information that we can identify from the shape. So the next piece of information that we're going to look at is polarity. And so what we're looking at with polarity is we're looking at the shape itself. So polarity can either be represented with a nonpolar molecule and a polar molecule. So if it's a nonpolar molecule, then we are looking at an even distribution or an even sharing of electrons. So this also means that we have a symmetric shape. Okay, so if we are looking at a nonpolar molecule, what we're going to see is that we've got an even distribution of electrons or even sharing of electrons throughout the molecule, and that is going to be reflected to us by a symmetric molecular shape. So by symmetric, we mean evenly distributed. Our outer atoms are evenly distributed around the central atom. If we have a polar molecule, it's kind of the opposite. So we're going to be looking for an uneven sharing of electrons, which is going to be indicated by an asymmetric shape. So these are our shapes that are kind of skewed off in one direction. So another way to look at this is that we have even distribution of outer atoms. And on this one, we have an uneven distribution of outer atoms. Now, the thing that affects the distribution of the outer atoms, like we just discussed in shape, is whether or not there are lone pairs. So when we talk about even distribution of outer atoms, those are our flat or evenly distributed shapes, like our planar shapes or linear. So we had linear and we had trigonal planar, and those molecular shapes are all flat and evenly distributed. And then we have tetrahedral that isn't flat, but that fourth leg is in even distribution with the other three. So all of those are spaced out evenly around the outer atom. So all of those shapes would indicate a nonpolar molecule. So then our polar molecules really are our unevenly shared electrons and creating an asymmetric shape. So there's some kind of uneven distribution of the outer atoms that is caused by those lone pairs. So this little note underneath here tells us that it's polar if there are lone pairs on the central atom. That's a little bit wiggly there. Sorry. Let me erase that because that did not come out very well for you guys. Let's try this. So again, it's polar if there are lone pairs on that central atom, okay? The other situation that could create a polar molecule is if the atoms bonded to the central atom are different. Okay, so this is two different scenarios. If we have lone pairs on the central atom, that means that we're polar. Or if we have one of those typically nonpolar shapes, but the atoms are different, then there is a possibility that those electrons are unevenly distributed between them. So we can end up with a polar molecule even if it is typically a shape that creates a nonpolar molecule. So the next thing that we can determine from here is whether or not, or rather, which forces are at play in the molecule. So the first type of forces that we can experience are called London dispersion forces. And London dispersion forces are experienced by all molecules. So London dispersion forces are experienced by polar, and non-polar molecules. Okay? Dipole-dipole forces are only experienced by polar. Let me get that in bold for you so that it looks a little bit more standout-ish. Okay, so dipole-dipole forces are these positive-ish areas and negative-ish areas that are experienced when we create a polar molecule. And we'll look at that a little bit more in the lab activity that you guys are going to do in terms of what that actually looks like. But this just means that it has a positive-ish end and a negative-ish end, and that those are going to experience forces of attraction between opposite charges. So the positive end of one molecule might attract the negative end of another molecule. And again, we are going to look at that in a lab activity that you guys will do. So then the last one that we have is called hydrogen bonding. And this occurs when hydrogen is bonded to one of three other elements. So we've got nitrogen, or oxygen, or the last one that is a possibility is fluorine. So when we have hydrogen that is bonded to one of these three, it is an extra strong force that's experienced because of the differences in electronegativity between them. So you have this extra strong force between them. So the last thing that I will say about hydrogen bonding, come back up here and undo whatever we just did. Hydrogen bonding is only experienced by polar or in-polar molecules. So when we look at our forces, if it is polar, it is going to always experience London dispersion forces and dipole-dipole forces. Then we check for hydrogen bonding. Does our polar molecule have hydrogen that is bonded with either nitrogen, oxygen, or fluorine? If it does, then it experiences hydrogen bonding in addition to the other two. If it doesn't, then we are left with just London dispersion and dipole-dipole forces. If our molecule is non-polar, the only force that applies to non-polar molecule is London dispersion forces. So this takes us down to looking at an entire example and everything that we can identify about it. So the first thing that we're going to start with is the Lewis dot structure. With the Lewis dot structure, we are going to do that first. We're going to look and see that we've got 2 hydrogens, each with 1 valence electron, plus an oxygen that has 6. That's going to give me a total of 8 electrons, which is going to give me 4 pairs. So that tells me what I'm looking for. So my central atom is oxygen. I'm going to bond it on each side like we have been with hydrogen. And then I look and I count everybody's valence electrons. Oxygen already has one accounted for on that side of the bond and one accounted for on that side of the bond. So that's 2. It needs 4 more. 1, 2, 3, 4. Now all 6 are represented. Hydrogen only has 1 electron total, much less 1 valence electron, so it's already accounted for right there. And it's already accounted for right there on this side. Hydrogen can have a total of 2, so 1 bond is all it can accept. Oxygen has the 6 valence electrons that it came with, but then sharing, it has 7 and 8. So we've satisfied oxygen's octet. So the next thing that we look at is we look at how many outer atoms we have. We have 2 outer atoms. And on the central atom, we have 1, 2 lone pairs. Remember, we only look for lone pairs on the central atom. So we can say that the shape that we experience as a result of having 2 outer atoms and 2 lone pairs is bent. And again, that comes from our table indicating what orientations of outer atoms and lone pairs indicate which shape is created. So the next thing that we look at is that shape a polar shape or a nonpolar shape? So we can take a look at the shape itself. The shape itself has oxygen in the middle, and it has hydrogen on either side when we bend it like it actually is. So we have our 2 bonds that are created there, and then we just have to be able to imagine that those 2 extra pairs of electrons are up there, and that's what is causing those 2 atoms to deflect downward. So we have to ask ourselves 2 questions. Is this a symmetric shape or an asymmetric shape? And to answer that question, we say, does it have lone pairs? The answer is that yes, it does have lone pairs, and it is an asymmetric shape. Therefore, it is polar. As a result, the last thing I need to answer is what forces does it experience? As a result of being polar, we know that it experiences London dispersion forces because everybody experiences London dispersion forces. And then it experiences dipole-dipole forces because all polar molecules experience dipole-dipole forces. And then lastly, we check for the special case of hydrogen bonding. We ask ourselves, do we have hydrogen? The answer is yes. And is it bonded with either nitrogen, oxygen, or fluorine? And the answer is yes, because hydrogen here is bonded with oxygen. So in this case, we also have hydrogen bonding. So for this example, that is everything that we can know about it. We can do its Lewis dot structure. We can tell how many outer atoms and lone pairs does it have. Therefore, what shape it is. And then sometimes it helps to draw out what that shape actually looks like to determine whether we have even distribution or uneven distribution and whether or not it's polar or nonpolar. In this case, it was polar. As a result, then, we indicate what forces it experiences. So on your test, this is everything that I can ask you about a particular molecule. Remember that this only applies to molecules. So this is only going to take place in a covalently bonded compound. We are going to work in groups on the remaining examples, and I'll be circulating to help. If you are out and have questions, please make sure that you reach out to me and we can set up a meeting time to go over those. Thanks, guys.